All right, let's get started. Let me make sure. What do we have on? Okay, great. So quickly, Elder Stevenson is speaking in the devotional tomorrow, so don't miss it. Also, my son, who got called to Korea, he gets to go right to Korea on his mission. So he leaves in 2.5 weeks. So he's done with the MTC, finished Saturday. He was supposed to fly out this Thursday to New York, Syracuse, New York. That's where he'd been reassigned. They told him, nope, we're canceling those orders. You're heading out in 2.5 weeks. So he gets 2.5 more weeks to hang around with us and teach us Korean. So it's nice. Yeah, he's so excited to be able to go to Korea. And it's just exciting that more people are going to these countries because they are dying. I've got a nephew in Spain, and they're just dying. I mean, they just are closing down areas left and right. They just don't have the support they need to get things. They're asking missionaries to extend, like to just keep some life in the mission. And so hopefully this is the beginning of a good trend. All right, who'd like to offer a prayer for us? Yes, Braden.
Our Father in heaven, we thank you this day for our opportunity to gather here to learn linear algebra with Brother Corey. Please bless us that we may have the Spirit to teach us and to help us understand these concepts. Help us to know how we can apply this in our lives and help us be ready for the test. Bless Brother Corey that he'll be able to teach well, what he's prepared, and according to our needs. We say these things humbly in the name of thy Son, Jesus Christ.
Amen. Thank you very much. Homework's over here. So 3.6 is the next section. It's on linear transformations. We might even get a chance to touch on it today. But we've already been talking about linear. We've already introduced linear transformations and used the intuitive idea of transformations and some of the other stuff that we've done. I highly recommend you watch the 3 brown, 1 blue videos if you haven't already, especially up through 8, because that really captures a lot of the essence of what we've talked about and in terms of transformations. His whole video is about making sense of matrices and linear algebra from a transformational perspective. So he says it's not a mathematical perspective at the beginning, but it is mathematics because he doesn't use any contexts to make sense of what's going on. He still views it as in kind of an abstract world, but they're still great videos. They're still awesome videos. And then 13, that's the other one I have listed there. That does what's called the change of basis, which is really what we're doing today in terms of coordinates. So I should have actually had you watch that before. He goes a little bit more in depth, and we'll do a little bit more of that change of basis thinking come next week when we get into eigenvectors and eigenspaces. So, okay, let's go ahead and start with these problems. The second problem was a midterm problem from last semester. So I just pulled it right from that exam. One thing when you do a contextualized problem is you have a lot to read about the context, so it is kind of long. But so let's go ahead and take several minutes for you guys to work on problem 1 and problem 2 here.
still trying to figure out how to start. I know for like for the examples, they were always just where like the number of components and the V would always be
That'll be the same.
the
But I'm almost there.
Oh, you did the thirds. Yeah, but it still goes away anyways, because you've still got.
All right, we have people that are going to go put the work up on the board for these two problems. So you can compare it to what you had. But also, if you've got questions, holler. So you guys were doing really well. Saw some groups that were just doing awesome. Really had nice ways of thinking about this. All right. Okay, let's get started up here on this problem. So this is the first one. So we have a basis, a different basis. I'll finish it for you. I don't know. Where this? That's going to be V. No. So the question is, you have this basis, and it gives you two vectors, and they're column vectors. And the question is, what are the coordinates with that new basis to find V? So here's V right here. But this is also V. Both of these are V. This represents the exact same information, the exact same point on the grid. What's different is the basis vectors that we're using to get there, the way we're describing the grid. So if we think of x, y's, and z's, if we think of this, if we think of our 3, that's where this lives, right? This point, 2, 1, and a -1. We have this standard basis where this is 1, 0, 0, 0, 1, 0, and 0, 0, 1. And that 2, 1, -1 means I'm going out 2 of these. I'm going this way in one of those, and I'm going this way in one of those. So it's that point, okay? So that's what we're comfortable with, okay? We're already used to thinking about that. But the span of these two vectors, is a plane that slices through R3, okay? So it's a two-dimensional plane. I don't know what it looks like. I'll just say something like this. And we're saying that this point is in that plane. Well, we hope it's in the plane. If it's not in the plane, we can't find the coordinates, and you'd end up with no solution here. You'd have 0, 0, and then a non-zero. But we end up with 0 here. So the way to answer this question is how much, the coordinate thinking is, like I'm thinking if we hadn't solved it yet, I can think how much of this vector and how much of this vector do I need to get this vector? And these are the coordinates, Okay. These. If you tell me how much of this vector, if you tell me what those values are, then I know the coordinates. So in terms of this plane, what happens is I have a new set. I don't know what they are, maybe like this. And so with these two vectors in this plane, then I can describe this point with those two vectors. So what is it? 2 of these and a -1 of those. There was some transformation that happened. It's just the angle of the board that makes it look like it's, that those aren't parallel in the same size. But yeah, the idea is like there's 2 of these and there's a -1 of those. There, see? Perfect. So, so that's the idea. So now I can still get to the same spot. We've just described it in 2 different ways. Okay? 2 and a -1. One nice thing about this is we just did a compression of, we lost a third, with a third less data, we can portray the same information. That's one of the uses of getting a new basis is that you can portray the same information, or almost all the same information with a lot fewer coordinates, a lot less information. Almost the same information with fewer. I want to say information, but it's not the same. Fewer values there. Okay, questions about this? Or questions about coordinates in general? Bases in general? Danny.
Maybe we're going to continue here, but I was wondering, what if the point hadn't line? What if the point wasn't in the plane? How would you go about solving it?
Okay, so that question was, what if the point wasn't in the plane? Great question. So what if I gave you 2, 1, so 1, 1, 0, 0, 1, 1, and I gave you 2, 1, 0, 2, 1, 0, 2, a -1. Nope, what did I give you? What was the problem? 2, 0, and 2, 1, and a -1. All right, so we'll just say 2, 1, and 0. And so you can set up the same problem. You start row reducing. I get 1, 0, 2. I get to subtract the -1 there. So I still get 1. I get a -1. And then I can to get rid of this one, I have to multiply this by a -1 and add. And I'm going to end up with that. That's an inconsistent solution. So there are no coordinates. I can't get there by telling you how much of this and how much of this vector and how much of this vector. It's outside the span of those two vectors. So, does that help?
Well, yeah, I was just thinking, wouldn't you want to approximate?
Oh, great. So, yeah, if you want to approximate it, this is a fundamental problem in science and data. It has a name. It's known as regression, which a lot of you have already seen. But basically, regression is trying to find the nearest point on a subplane that's closest to a vector, or to a subspace that's closest to a vector that isn't in the subspace. And so you would project down. Yeah, so if I've got this thing and I've got a vector here, then I would project it down perpendicularly and find out what that point is. And then I would describe that vector in terms of my basis vectors. So, and those are the regression coefficients you get for those of you that do regression. So I'm hoping to dive into that sometime later. It's not in the curriculum, but it's so cool. So, and so useful. Yes?
Despite the fact that it's inconsistent, is there anything significant about the solution if you take what you wrote up on the board there and just remove that inconsistent row and just left it there? Is that like the projection of it or something cool like that?
Oh, so that question was, is there something we can do here with this 2 being 2 of the first and a -1 of the second? Does that say something? Probably. I haven't thought enough about it. So, yeah, you could go back and say, well, what do I get in terms of if it's 2 and a -1? What do I get for each of those? This might tell me that I'm off by 1 in that direction, but it still might not be the closest spot I can get. So probably the closest I can get in just the XY plane, but not the XY and Z plane or something. Nice question. I haven't even thought about that question. That's nice. Okay. Other questions about this? Or bases or spans or coordinates in general? Yes. Okay, so that question was, what's the simplest definition you can get for a basis, and what's the practical application? So, so the simplest is it's your building block. It's these like black vectors or the blue vectors. It's the way you describe. They're like the directions you're working with in your subspace. And if you're three-dimensional, you need three directions. Okay, so that's your basis, is you tell me those three directions if you're in three space, or you tell me those five directions if you're in five space. Now coordinates, once you tell me the directions, a coordinate is how much of each of those directions I need to go to get to any point in that subspace. That's all a coordinate is. And what's the application? Well, this next one is an application, or with these pictures. So a basis just gives you they're often just a different way to think about the same space. So here, in terms of, we can think about the number of pictures in terms of sizes or in terms of packets. So the bases are just, well, I can think about a size basis and I can think about a packet basis. And then the number of pictures I get, you can tell me, or we can communicate in either one of those. So the biggest application for bases is we're going to find out that any square basis has a natural any square matrix has a natural basis that makes a lot of computations really easy, and that if you think about it in that basis, then you can more fully understand what the transformation is that it does. So those are it's called an Eigen Basis. So in a lot of the technical fields, that's where it gets used the most. So is in terms of Eigen Bases. So, and people would argue eigenvectors and eigenvalues and eigenbases are like the most important thing you'll learn about in this class. It's like the fundamental thing to understand about matrices, and they're used all the time. Okay. So here the question. So really the same question is, how much of each of these do I need? Because this is packet A, packet B, packet C. This is how much of each of these packets do I need to get 6, 5, 28? This is 8 by 10s, 4 by 5s, and wallet. Do you guys know what wallets are? Yeah, so some people are saying no. Because no one carries wallets anymore, right? You've got all your pictures on your phone, so they're wallet-sized images that would slide inside your wallet, and they would have like photo carriers you could have inside your wallet, and so you could get them that size. But now you just carry everything, all the pictures on your phone, so they don't bulk up your wallet. So like it was a big thing to have a picture of your girlfriend or boyfriend in your wallet, right? So you can show everyone. Now it's just, you just text them a picture. Okay. So here you have this. So we augment it, because that augmented matrix represents the same thing as C1 times packet A plus C2 times packet B, C3 times packet 4. This is like really the same thing we've been doing for months now, equals 6, 5, 28. We're just using different language. Okay, so how much of each of these do I need to get this? Well, I can write that down as a matrix multiplication, a product, which represents this. The big thing now is we're talking about these coefficients differently, and we're thinking about what this matrix does differently. So these are the coordinates here. So we're trying to find C1 and C2 and C3. So we know how to do this. We augment the matrix. We row reduce. We get to here. We get 3, 0, 1. So I need 3 of A, packet A. I need to buy 1 of packet C. Okay. Nice. Questions about this? Do I have pictures of my girlfriend? Oh, once you have kids, then you send them to aunts and uncles and cousins, you know. Now you just post it on Facebook and everyone has it, but before you had to physically put them in envelopes or pass them around. So, and put them in this kid's scrapbooks and, you know, all that stuff. Okay, yes? Yeah, so that question, is that the same as finding the inverse and then multiplying it by this vector, right? So yeah, we could solve this system. We could solve the system of equations by finding the inverse of 1, 2, 3, 0, 3, 5, 4, 8, 16. Inverse, if I find the inverse and multiply by 6, 5, 28, then that would also give me 3, 0, 1. Okay? So the system before was, because we haven't written this out yet as a multiplication, 1, 2, 3, 0, 3, 5, 4, 8, 16 times, this was unknown, right? X, Y, and Z equals 6, 5, 28. So what you do is you multiply both sides by the inverse. Okay, so, and then that goes to the identity, and this gets you, this product you can do, and you get the 301 right there. So that's going to be important. We're going to come back to that idea. Yes?
To conceptualize the basis for our packets, is there any way that we can geometrically conceptualize that, or does it not really have like a, would it be like an entire R3 that is built by?
Yeah, so in this case, yeah, we have all of R3 to work with. Like there's two bases here. The 8 by 10s, 4 by 5s, and wallets, those are serving as the standard basis in this situation. Because each of these columns I can rewrite as, like A is 1, 1, 0, 0, 0 of 0, 1, zeros, and 4 of 0, 0, 1s. These are standard basis vectors, right? Well, I hope you. Like these are our x, y's are typical x, y, and what each x, y, and z represents. That's those are called standard basis vectors. In higher dimensions, they're 1, 0, 0, 0, or 0, 1, 0, 0. Like you can just list off down as many as you want. But in this case, this is 8 by 10s, 4 by 5s, and wallets. So they're kind of serving as our standard basis here. And so we can think about R3 as, we can think about it in terms of this basis, which is what we're easy at doing, or we can actually think about it as this basis, these columns. So they're different vectors. They're different directions that I'm working with. I can still get to any point in R3, but if I'm working with the packets vectors, you just whatever point you're talking about, you just have to translate. You have to tell it to me in terms of packets, like the 301. I actually have here. I have some things that will help here. Okay, so first I want to talk about transformational thinking, and then I want to talk about change of coordinate thinking. So first, we've talked about transformations, and one way to think about this, the transformation-wise, is I keep the grid the same. I'm still living in the exact same grid, okay? The exact same directions. I described both. I had to wake some people up, right? So they were, you know, eyes were drooping, other stuff. So the grid stays the same. I'm still dealing with kind of like the standard basis, or you can think about dealing with the standard basis, but then the vector changes. So I transform the connection here. I don't have my 301. Yeah, this matrix here, this matrix here will take 301 and move and transform it so it points to 6528. Okay, that's what this matrix does. Okay, we didn't know that at the beginning. We had to find out what this was, but now that we found it, I can put 301 there. If I multiply this matrix times 301, I get 6528. So I can think about this matrix as performing a transformation, and it would transform that 301 into 6528. It would transform anything in R3 to something else, to some other vector in R3. Okay, so that's transformational thinking. Coordinate thinking is different. So changing coordinates, the point stays the same. We're not changing the point like that goes from 301 to 6528. The point stays in the exact same spot, but we change the coordinate system. We change the grid. So in this case, let me make this a little bigger, which is a linear transformation, ironically. Okay, so this is from chapter 1 in your book. This is, remember the reading early on where I said, pay attention to this example. This kind of thinking is really important. We'll use it in the class a lot. So here we have the standard grid. So these, what we're used to, thinking Cartesian plane, but they also put on another grid where u and v are the basis vectors. So this point right here, I can think about as a negative 1x and 3 y's, where this is x and y. I can also think about it as a negative u and 2 v's. So a minus 1 and 3 in terms of x and y's, but a negative 1 and 2 in terms of u's and v's. So the point is exactly the same. I haven't transformed the point. I haven't transformed a minus 1, 3 to a minus 1, 2. I haven't transformed it at all. I've kept the point the same. I've changed the grid. So in terms of, this is our particular example with the picture packets. D here is 6, 5, and 28, okay, in the standard basis. So 6 wallets, or sorry, 6 8x10s, 5 4x5s, 28 wallets, okay? Each of these red ones represent the packet vectors. So the shortest one is A, it's 1, 0, 4. The second one is 2, 3, 8, and that represents B, and the longest one represents our capital C, 3, 5, 16. And coordinate thinking is, I'm not going to find the new spot after a transformation. I'm just going to find out the new coordinates with this new system. So now, if these 3 directions are these 3 red vectors are the 3 directions that I am working with in R3, then the question is, how much of each of those directions do I need to get to D? And we already know it's 1 of C, and I needed 3 A's. So over on the right, I lined up 3 A's at the end of the C, and you can see, sorry, that it lines up to D. So I can think about that as 6, 5, 28 in terms of X, Y's, and Z's, our standard basis, or I can think about D as 3, 0, 1. One of the red C's and 3 of the red A's. So I can think about it either way. So you can think about it as a transformation, like that matrix transformation, or you can think about it changing the basis that we're working with to a different basis. And sometimes one is valuable, so other times others are valuable. Okay? Danny.
Just in that transformation thinking, would we have a way, if you gave us the original vector and the transformed vector, to find what the transformation matrix was?
Yeah, that is the next section. There's a slick way to do that. Yeah. So, yeah, that's 3.6. We're going to talk about how to do that. So, good question. Oh, for those online, the question was, is there a way to find the transfer if you know where the vectors go under a transformation? Can you figure out how to find the matrix that does the transformation? You do have to have enough information. If you just know one vector to one vector, there might be lots of transformations, like in R2 or R3, where that can happen. So you'd need to have at least two vectors. Yeah, 2 vectors transformed in R2 or 3 vectors transformed in R3 to know exactly which which matrix that would be. But yeah, we'll talk about how to do that next time. Okay, other questions right now about any of these topics? Okay. So I'm going to delete this one. So here is, this is just conceptual. We're not thinking about pictures. We're back to our peanut butter, bread and jam, protein, fat, and carbs matrix. So we're calling that P. So 2 questions. Without solving, what vector does P times a vector that's in the peanut butter, bread, and jam basis represent? And if that's hard, you can just think about P times any V. You don't have to think about it particularly in peanut butter, bread, and jam. Just P times any three values, any packet of 3 values. So what vector does that represent? Meaning, after you do that multiplication, you're going to end up with a new vector. Okay? How do I make sense of that new vector? Where does it live? What units should it have? And then without solving, what multiplication will transform a protein, fat, carb into a peanut butter, bread, and jam? If I have a protein, fat, carb vector, what can I multiply it by to get it into peanut butter, bread, and jam? So talk about that, think about it, and then talk about that. Okay. All right. If I take any vector and multiply it by this matrix, 8, 15, 7, 4, 1, 8, 0, 0, 13, and I take any matrix here, any vector here, then the natural way to think about this is, let me get some, I'm really sorry about the 2 P's at the beginning. I should have reordered over here. So it's easy for me to think about this in terms of protein, bread, and jam, because I can rewrite this multiplication as 1 times this vector. So I can think about it as 1 serving of peanut butter, 2 servings of bread, 3 servings of jam. That's a really sweet peanut butter bread sandwich. Okay, but some people like it that way. Okay, but that's peanut butter, bread, and jam. And then what I get out is something in terms of protein, fat, and carbs. So in this case, it's going to be, let's do the first thing. This is 16 proteins. Okay, and then some other stuff. So this matrix multiplication, I can think about it as transforming 1, 2, 3 into a whole other vector and stretching it out and rotating it or whatever. But I can also think about it as, hey, this multiplication, it didn't change anything other than it's the same information, just changed it from me thinking about peanut butter, bread, and jam to protein, fat, and carbs. So it just changed the basis for me, just changed the coordinates of that same point. So 2 different ways of thinking. Yes? That's right. So that question was, when you say change of coordinates, you mean they'd both be pointing to R3, just with different, what did you say at the end? Yes, with different directions. So let's do R2 really fast, because that's a little bit easier. But yeah, so I can pick these 2 as my standard, but I can also pick these 2. And I can describe any point on here. I can describe any point in here with either of these. So to get to that one, yeah, maybe 2, maybe 3. So that could be 2, 3. That's 2, 3 in the black basis. Okay. And oh, this one's going to be kind of fun. Well, I can go this way, this way, this way, this way, this way, and then now a negative, a few of those. So a negative 1, 2, 3, 4, 5. So a negative 5 and a negative 3. So yeah, so it's the same point. I'm just working with different directions here. So why are you guys laughing? This is hard. Oh, like it's the angle of the board. It's hyperbolic space. You know, it's curved and okay. All right. Yeah, physicists will know what I'm talking about. Okay. So yeah, it's the same. Yeah, we're talking about the same point. It's just we're starting with different directions. You're telling me how many of each of those directions I'm going to. So, yeah, good question. Okay, there was someone else that had their hand up. Okay, so we can think about this as a function also that takes a process that takes in peanut butter, bread, and jam coordinates and spits out protein, fat, and carb coordinates. So that's what the multiplication of this matrix will do. The last question was, what if I wanted to go the other way? What if I had protein, fat, and carbs, and I have the coordinates in protein, fat, and carbs, and I wanted to find the coordinates in peanut butter, bread, and jam? What do I do? So there are 2 ideas out here. Someone went like this, but I also serve. So you could think, well, the transpose, right? You might try, oh, let's do a transpose. So I have peanut butter, protein, fat, and carbs, peanut butter, bread, and jam. Okay. You can try that. It doesn't quite work out unless you have a very, very special set of matrices, and that we'll study later. So the transpose isn't quite right. Yes? Multiply it by the inverse. That's right. So this is P. So we can multiply if I already have PFC, my protein, fat, carb, I can multiply that by P inverse. And then I get my peanut butter bread and jam. Okay? So one of the things to understand here is that if I have my peanut butter bread and jam, if those are my columns, then I multiply it a vector, I'm going to get out of this matrix. I'm going to get out of this basis. So multiplication of P gets me out of peanut butter bread and jam. If I want to get back into peanut butter bread and jam from another basis or a standard, what we'd call the standard basis, then I want to multiply by the inverse. Inverse gets me into that coordinates into that new basis. Multiplying by this matrix where the bases are the columns, multiplying it by this one gets me out of that basis into the standard basis. So in this case, the protein, fat, and carbs represents our standard basis. Because like this 8, 15, 7, so a peanut butter serving is 8 100s plus 15 010s plus 7 001s. So this is the clue that says this is the standard basis is the protein, fat, and carbs, because this looks like our X, Y's, and Z's. So, okay, we're over time. Thank you very much.